Good evening, everyone. I think we're live in the event now. I can see a number of attendees. It's 5:45. I think I'll just wait another minute for people who may just be trying to log in, and then we'll begin proceedings. I can just see a couple. Yeah, I can just see a few more people joining now. That's good. Yeah, hang on, 45. Right, I think the numbers look like they've stabilised, so I think we'll make a start. So, as I said, good evening, everyone. I'm Jason Greenbridge. I'm the chairman of the IMechE Railway Division Midland Centre. And it's my very great pleasure tonight to welcome you to the third lecture of the session, which is our Railway Division Chair's annual address. So before I introduce our chairman, just want to say I hope everyone's well and their families are well in the current COVID-19 situation. Obviously, with another lockdown at the moment, I hope everyone is okay. And I guess one of the upsides is we are getting used to these remote lectures and probably getting a little slicker at doing them. But yes, I do hope everyone personally and friends and family are okay in the current climate. Before I introduce our chairman, I'll just mention logistics. So everyone who's an attendee, their camera is off and they are muted. So we'll run the lecture in a minute. I'll do the instructions and then hand over the lectures. If you want to raise questions for the question and answer session at the end, can you please go into the chat function? And if you set your chat to all panelists and enter your question, those questions will appear in a line, and at the end of the lecture we will go through as many as we can go through in the time we've got available, and we'll get those answered. So the chat function is the button to use at the bottom right hand of your screen. So I'd now like to introduce the chairman, which is Felix Schmid. So Felix, for those who don't know Felix, just a very brief introduction, graduated from the Swiss Federal Institute of Technology in Zurich with a Master's of Engineering in Electrical and Electronic Engineering, a career spent early as a software analyst before moving to the UK and spending 3.5 years designing control systems for electric locomotives at GC Traction as was. A sabbatical back in Switzerland, followed by a return to the UK, where Felix was first at the University of Sheffield, where he established what I know as well, the MSc programme in Railway Systems Engineering, and in 2005 transferred the programme and himself to the University of Birmingham, where he's been since. Felix is just retired and is currently the Professor Emeritus of the Railway Systems Engineering at that university. Felix's presentation tonight is titled The Long History and Exciting Future of Railway Systems Thinking. I won't say any more about it, and without further ado, I'll hand over to Felix and look forward to hearing what he's got to say.
Thank you very much, Jason. I want to assure you all that I'm wearing the badge of office, which is the Institution of Locomotive Engineers badge, in fact. And I will display it later on.
Welcome to my chair's address for the Midland Centre of the Railway Division of the Institution of Mechanical Engineers. My name is Felix Schmid and I'm the chairman for 2020-2021. I'm going to talk about systems thinking for the railways, and this talk is very similar to those which I give to the other centres. However, I'm going to have a very short passage, which is specifically for the Midland Centre. Look out for it. It may have something to do with the bank.
I hope you heard that, because WebEx sometimes plays tricks, and I hope you can hear me now. This is a picture of me impersonating Stephenson. Some people have said it's Stephenson impersonating me, but that's a bit too much. My interests are in systems engineering, systems thinking, railway traction systems and railway control, and of course quite a lot on ergonomics. I'm going to talk quite a bit about railways as a complicated and complex system. And I'm also going to talk about the system of systems approach to thinking and designing railway organizations and systems. And what I want you to take away from this talk is that we should embrace change. We should not try and forestall it. We should always think of the value of people. And I also want you to sort of think that education is something worthwhile, no matter what people in politics sometimes say. So it's going to be an educational talk, so that's an apology. I'm going to talk, as I said, about systems, a bit of history, of course. I'm going to describe what the system of systems is and what the emergency properties are. Then I'm going to talk quite a lot about complicated and complex systems, and those people who have been on my MSc programs will probably have enough of that already. And then I'm going to talk a little bit about Perrot's normal accident theory, and something which might be slightly provocative. Trying to prevent failure is not the sound strategy, because there's too many unpredictable elements there. Now I'm going to talk about the V system life cycle and the complex system adaptive cycle, and at the end a bit on me, but more about what I have done over the past X years. So the definition of a system is basically that it's an entity, it sits in an environment, it's influenced by the environment, but it also influences the environment. And it may have just a single person or multiple purposes. Some people describe it as a group of interacting or interrelated entities. So if they have links between them and they influence each other. And the system is described by its spatial definition in its temporal boundaries. And you can describe it by its structure, its architecture, etc. But the most important thing about the system is that it does something. It might also be a set of principles or procedures according to which you do something. And, well, a railway, of course, has the purpose of transporting people and goods safely, economically, and timely from A to B. And because I always like a little bit of history, I start with some history. Today's railways really were born in Germany, in the mines, when people discovered that if you had a smooth running surface and you had a guidance function, in this case here, it's just a pin between the two planks. And so down here is the pin, and that guides the vehicle along the track. And you need less space, and you can transport more with less effort. So it was a very attractive solution. And yeah, of course, somebody had to take this to the UK, and it was German miners who brought this about 1600 to the Lake District, from where the technology spread to quite a lot of mining areas. The early railways which came after this were rather rustic, and they often were described as railways, railroads, so the equivalent of a road with rails, tramroads or tramways. And the word tram actually comes from a German word trammel, which is a piece of wood or a log. And of course, with a railway, that's quite an obvious use of the word. So today's tramway is actually a German a wooden way. Now, what was the first really deep insight in terms of railways was the realization that by having the wheel on the rail and having a substructure, you could accept a very high load. And today's dynamic wheel force on a single wheel is about 350 kilonewtons, which is permissible. And if you think about that, that's 35,000 bags of sugar. That's quite a lot. And it's all balanced on about a square centimeter of area. Now, when you actually look at that in a bit more detail, then you can see that there is a huge pressure between the wheel and the rail. But when you get down to the level of the natural ground, this drops incredibly. So the pressure at the railhead is something like 280 bags of sugar per square millimeter. I think that's quite an evocative type of figure. And by the time you get down to the bottom of the sand blanket, that's only 0.35 Newton, or about 35 grams per square millimeter, which is fantastic because it allows you to run railways over swamps. It allows you to run railways on ice in some cases. So when the first people started to think about locomotives, they realized that this might not be so easy. So Trevithick, Burton, Blenkinsop, Eisenbaching, the Brunel, and many others were convinced that iron wheels on iron rails would inevitably spin and not do anything at all. I hope you can hear this. This is a replica of the Coalbrookdale locomotive, which was designed by Richard Trevithick. Well, it had a problem that it had only one cylinder and therefore and one piston. Therefore, if you didn't get it to swing properly, it wouldn't actually do the job. But as you can see, it did work. And the big thing which Trevithick brought to railway traction, and I'll come to that in a second. You can see that the blast of steam which comes out of the chimney is rhythmic, and basically it was created or is created by the steam, the exhaust steam from the pistons going into the chimney or into the smoke box and thereby creating a vacuum. And what Trevithick wrote to a friend of his is the fire burns much better and when that is done, and that basically it increases the power level and the use of the coal very significantly. He didn't trust the adhesion between the wheel and the rail, so he had his wheels serrated, which caused some problems. Because his second locomotive, Catch Me Who Can, he took to London to demonstrate in a circus effectively near Euston Square Station. And the problem was that because of the serrated wheels and because of the nature of the rails, which were cast iron rails, they broke regularly, the locomotive derailed. There were no deaths, but it was not seen as a big success. So Trevithick emigrated, and that was unfortunately the end of his career in the UK. Now, John Blenkinsop patented his own system in 1811, and he basically had a pinion which was driven by a two-cylinder or a two-piston engine, so much more likely to work than Trevithick's, and it engaged with a rack along the rails, and so it was the rack and pinion system that we find today on mountain railways and which was later adopted by Marsh, Rickenbach, Abt and others. Now, the steam carriage worked really well. It ran for about 8 or 9 years before they converted the railway to a normal adhesion-based railway. Now, William Burton was even madder to some extent. So in 1813, he built this locomotive, which was basically a walking horse. And it was quite successful. As you can see, it managed to go up gradients of up to 3%, which is very steep, and especially for the time. The drawback was, or the problem was, that somebody tied down the safety valve because it kept emitting steam. The locomotive blew up because it was overfired, and they killed a few people. So that was the end of the propeller or steam horse. In 1812, so that's just a year after Blenkinsop, Christopher Blackett had asked his colliery supervisor, William Hedley, and Timothy Hackworth, the foreman blacksmith, to experiment with adhesion because he thought it may well work, because before that everybody thought that only the mass on the locomotive could be carried or pulled by the tractive system. So you can see here the experimental setup, a wagon basically with cranks and 4 people, 2 on each side, cranking the vehicle forward. And what Hedley managed to demonstrate was that adhesion allows you to haul more than your own weight quite conveniently. and he produced a very interesting scientific paper about it. And I would say that Trevithick, together with Hedley, is really the father of railway traction, or the fathers. And he found that adhesion works really well through his experiment. And I mean, the most difficult railways currently running are the old Lisbon trams, which have got a gradient of 12%. And around tight curves, they can achieve 13.5%, basically because they just jam between the rails. Now, Stephenson took these two principles together, that is the steam into the smoke box and the adhesion principle, and he built a number of locomotives in 1822, so well before the Rainhill trials for the Hetton Colliery. And one of these locomotives is shown here in 1903 or 1905, but it ran until 1912. So that's probably one of the longest lasting locomotives, 90 years, less than probably a few days. Now, the real next stage was the rocket, which Stephenson built for the competition between Liverpool and Manchester. And the important point about this was not just a question of speed. The previous steam locomotives had gone quite slowly, but rocket could go at speeds of up to 30 miles per hour or 48 kilometers per hour, and it achieved this several times. On the third day of the tests, rocket covered 112 kilometers, and reliably, no problems. All the other locomotives who were in the competition failed. Now, because we're in Derby, I thought I'd put in some art, and this is a picture by John Cook-Bourne, who painted railways as they were being built. And this is the Bowl Hill viaduct between Tamworth and Wilnecote, so it's just south of Tamworth, and this is one of the earliest of his paintings of that line. And it just shows that the railway fits into the landscape, and I really like John Cook-Bourne. But let's get to the systems of systems issue. A system of systems can be described as a set of large-scale integrated entities. Each of those is a system potentially. They are heterogeneous, so they're all different. They can be operated on their own, but they are networked for a common goal through emergent properties. And I've read that out because I think it's quite a good definition. And some people would say that nature is an example of a perfect system of systems. This is a picture which we took this summer during a walk. And what it shows is that nature deposited a seedling of a tree on this rock. The tree grew quite successfully. Well, then there was a very strong blast of wind, and the tree succumbed to it. And I've got another picture from previous summer where Bridget and I were walking in Switzerland, and what you can see here is a tree which was effectively suicidal. It grew in a gap in a rock, and as it grew, it slowly split the rock off the surface from where it was lying, and the tree and the rock fell over, and that was it, the end of it. And basically, once established, trees have no options. So nature is not a perfect system of systems. It works very much by accident and by statistics. Most trees are successful, but some of them are very unsuccessful. Now, in general, technical systems are defined and designed by people. Now, sometimes people get it a little bit wrong, and they make things too complicated. So, Crossrail, or soon to be the Elizabeth line when it's finished, is a system of systems, and I'm only showing here the train control system or the safety systems, with a legacy system on the east side, a legacy system on the west side, ETCS to Heathrow Airport, and then a CBTC system through the core. And about 2 days ago, I read a very nice piece by Mark Wilde, who is now in charge of the project, saying, please, please, HS2, keep things simple, because then we can understand them. If you have something which is too ambitious, then your system is not going to be easily delivered. So there are some definitions here, and people sort of think that system of systems are really something very new. And the characteristics I've listed here on the left-hand side, they're generic characteristics. It's something, a contribution from Rhiannon Evans and Duncan Kemp, who worked with us at the university. And an important point is that a system of systems is managerially, developmentally, and operationally independent. So all the components have got their own individual lives. In general, the requirements evolve very quickly. There's usually lots of stakeholders, and they often have conflicting needs and little incentive to work together. And when all these things work together or try to work together, you get new properties, which you then have to manage. They're often geographically dispersed and connected through a network. And on the right-hand side, I'm basically talking about early GB railways. That's again a slide from Rhiannon. So there were 150 separate railways with their own owners and operators. The network grew very quickly, the services grew, the performance had to improve. There were lots and lots of stakeholders, and the cross-network travel meant that there were new requirements for ticketing, new requirements for technical compatibility, etc. And eventually, of course, this system of systems spread across the whole country and was connected through this physical rail network, until it became British Rail in 1948. And well, even then it wasn't fully unified, really. Now, at this particular point, I want to introduce somebody who I would consider a hero of mine, Sir Arthur Percival Heywood, who lived at Duffield Bank near Derby. He married a lady called Muriel in 1872, so he was still quite a young man. He had studied mechanical engineering at Trinity College and got a master's degree in applied science in 1872. And I will come back to that at the end of my talk. He built 3 famous locomotives, and he's portrayed here with the first one with Effie, a very small locomotive, and something which not many people know, he was also the founder of the Central Council of Church Bell Ringers. And I think we've got at least one of those in the audience. Now, why is this relevant? Well, for several reasons, as you will see. Sir Arthur Heywood, decided that you could actually do things on a much smaller gauge than other people. Brunel had built his railway at 7 foot, and here is a sort of list of different gauges, and that down at the bottom, 15-inch, the Duffield Bank Railway. Well, what he actually wrote is a book in the end, which was called Minimum Gauge Railways, and that's what he had built. And so the 2 other locomotives are on this picture here, an 060 and an 08 locomotive for 381 millimeter gauge. That's so tiny, but in his view, this was a fully functional railway, and he had a big circuit near his house on Duffield Bank. And what he actually came up with was an arrangement with radiating axles in order to be able to run through very sharp curves. So here on the right-hand side is the position of the wheels straight, and on the left-hand side is the position in a curve. And of course, that gave him a much better performance. Very, very clever arrangement, which was later on copied by other people in Germany and elsewhere. So I'm going to talk a little bit about this later, because he said a lot of things about railways, but the most important point was perhaps no great care was taken in the details of the construction of Effie. He just wanted to try things out, and he used a lot of stuff which had been lying around in the workshop. There is one point which I'm unfortunately having to admit. The fortune on which this work was built was largely obtained from slavery, but it wasn't Sir Arthur Hayward who did this, it was his ancestors, and well, I think we have to excuse it to some extent. Anyway, as Sir Arthur realized, railways are actually quite complicated and complex. And on the right-hand side here, I've got a number of elements of the railway. And I'm going to first of all highlight the complicated ones. So organizationally and physically, the railway is very dispersed. So it's actually difficult to manage people who work or operate along hundreds of miles of railway. We've also got very many different component types. We've got diversity of components and diversity of the organization. So you need many different skills. You have many different funding models, and you've got lots of different materials and asset types, etc. So these make railways complicated, but it's not impossible to manage them because you can list these things. You've got group procedures, and with those procedures and the databases, you can manage the system quite well. Now, there's also complex aspects, and if we start on the left-hand side here, we have got the variability, which is probably the most important one, physical variability and organizational variability. People don't always work exactly as they should. Third parties intervene or make mistakes. And of course, the ground may not be stable. There's weather and adhesion issues. And the other complex elements are on the right-hand side. The wheel rail interface, pantograph overhead line, timetables, rosters and schedules. If you don't have a train, a driver and track access at the right time, your railway does not produce a service. And you've got interactions between the wheels and the rails, between the points, etc., and the processes, which also make things very complex to manage. And the only time you can do that is right at the beginning. This table here, I'm not going to talk about in great detail, but basically what it says, there are some elements which are very complicated to manage, and there are lots of elements which are complex, and we'll see a little bit more why that matters in a moment. You've probably read all this already. Interdependence has been created as a term by McKechnie at University College Dublin. He has not written a lot, but I've sort of taken him as my guide. So we've talked about complication, lots of different kits, lots of different people, lots of different areas, etc. And the dispersion, of course, and we can manage that. However, it's not always so easy, but it just takes time. So this is an example of both dispersion and diversity from Richard Stevens, who has just finished his MSc program at the University of Birmingham and gone back to Australia. And this is an example from the state of Victoria. There are 2,200 switches and switch machines around the country or the state. And you can see there's about 35 different types, and they're all significantly different from each other. And somebody has to manage that. Some of them are in very small numbers, others are in very large numbers. Now, wouldn't it be nice to just overnight replace them all by a single type? You can't. It's too expensive and it's too high risk. And so railways have to live with heritage, with old equipment and new equipment in the same time. But if you manage it properly, it's not the problem. So 29 different types. I was wrong, it's not 35. Anyway, complex aspects I've talked about as well. It's about the close coupling of the subsystems, wheel and rail, timetables, schedules and rosters. And there's also interactions with systems that are not under the control of the railway. So the weather system, the other stakeholders in the railway were all influencing what's going on. Now, variability is a very important issue amongst these. And this is a picture which also got from Australia, which shows what happens when things change dramatically. And so delivery is what we call reliability in the UK, the number of trains you actually run. Punctuality is what we also know as punctuality in the UK. And you can see punctuality shot up during the start of the COVID. And of course, that's because passengers are a highly variable element. And that's a very useful lesson. If we can make the passenger more reliable, and there are ways of doing that, then your railway is going to be more reliable. Now, and as I mentioned, tight coupling and interactions with systems which are separate to the railway, over which we have no control. And Charles Perrow came up with this theory called the normal accident theory. Now, that doesn't mean that it's an accident type which happens every day. It isn't something which happens all the time. It's basically, regardless of how much effort you make, eventually an incident will turn into an accident by passing all the barriers which you have created. And in general, creating technical barriers against accidents does not work very well, because most serious incidents have somewhere organizational roots. And the best way of reducing risk is by avoiding overly complex technology. And here is an example, to my mind, of a normal accident. Since 2007, there have been no accidents in the UK where passengers were killed in a movement accident. And this summer, all of a sudden, we had a very, very serious accident. And I call this a normal accident because lots and lots of things came together. Because the railway is so tightly coupled between the wheel and the rail, it led to a derailment. And so, yes, there is a potential to blame somebody for it, but I don't think that's productive because it was not predictable in any possible way. Because basically, complex systems don't follow predictions. They respond to events in their context. They respond to component senses. They adapt as the environment changes. They adapt to other agents in the system. And they evolve and specialize and generalize. And what we can see here is, of course, the way in which life developed on Earth. And that's a very typical example. So what I said before is something about preventing failures not being a sound strategy. And Brian Kitchens at the conference last year came up with 3 reasons why it's difficult. First of all, comprehension. Incidents can't be fully comprehended. They're fraught with uncertainty. And if you do something to change, to prevent things, then that will not necessarily help. So at Stonehaven, the accident was probably caused by some well-meaning decisions in 2010 of building a better land train. And therefore, that concentrated in the end the stones which were ending up on the railway. The second thing is understandability. Managing the small stuff does not prevent big incidents because there are no direct causes. We don't find the causes in general, we construct them after the event. And what I'm showing here is the accident at Llangenech, where a wheel set or a whole bogie was braked and the train moved. The bogie started to become extremely hot. Eventually it derailed and it set the fuel on fire. And there was a system which should have detected this, which was a hot axle box detector, but it didn't do anything because it was only supposed to measure the hot axle box, not the wheel. And the third point which he makes is that it's not predictable. Learning from the last incident will not allow you to predict the next one. Complex systems are not deterministic. The state can't be precisely or repeatedly foretold. And of course, the example of flooding is a very key example in this area. And what he says is that both success and failure have the same genesis. When during normal work, you get performance variability, and to deal with that, some people will do workarounds or they will do things which are not compliant. And it leads to success. Fantastic. Now, the same actions can actually lead to failure. And the example which Ryan gives is that of a helicopter landing or not quite landing in the Alps in order to pick up an injured skier. The helicopter hovers, the blades of the helicopter go into the snow and whirl up the snow. The person gets in, the companions get in, helicopter goes back up in the air. Success. Now, had the same thing happened and there was a lump of ice or a rock in the snow, the helicopter would have hit the rock, it would have failed, people would have been killed, and the pilot would have been determined to be guilty, and if he survived, he would have been taken to court. But in both situations, the change in behavior was exactly the same, but in one case, it got a failure. So if we try to constrain performance variability in order to avoid things on the right-hand side here, we might actually at the same time affect our ability to achieve success. And in most cases, we achieve success. So we have to be very careful. And Ryan also offers some approaches on how to think about incidents. Sakichi Toyota says you should ask 5 whys. So you ask, why did the train derail? Then when somebody says, oh, it hit some stones, then why were there stones? Then, well, why was the drainage arranged in this particular way? So very quickly, you exclude a lot of possible answers by doing this. So what Ryan says, if you want to learn lots from incidents, then ask people how, not why. Ask people to describe how they experienced the situation. Ask people how things happened, because there are no root causes when an incident starts to happen. And try to make sure that things go right rather than preventing them from going wrong. So learn about things that go right and try and keep doing it that way. And relabeling incidents into surprises might actually make you more aware of what's going on. And I've mentioned the issue of Australia, of the trains without passengers. We have to observe the same at Manchester Deansgate, where the train service is suddenly working reasonably well. But now, I promised you to talk about the system life cycle V model, and this has emerged from a discussion with Alex McGrath in Australia, and I'd like to thank her for that. So when you have the task of designing a new system, you usually start with a concept right at the top here on the left. You then define the system and the application conditions. You have system requirements. You apportion the requirements to different parts. You design the parts. You make them. You install them. You validate them. You commission the system. You accept it, in most cases after a short time, in some cases a lot later. Think of the airport at Berlin, Schönefeld or Brandenburg. The system then runs, and eventually you have to decommission and dispose of it. And between each of those stages, you have a phase of verification where you try to make sure that you've done the thing right. And here again, that you have done the installation right, the system validation right. And in between, you're checking that it's not only you have done the job right, but you have actually built the right system. So the blue area here is understanding the problem. You have the concept, and that lends itself very much to a fairly systematic approach. Implementing the system is a very important second phase, and then operating the system is the third phase, which is very important. Now, when we actually do this, we go through phases of systems thinking and systems engineering. And to me, this side of the V cycle deals with complication. It's systematic, it uses databases, it uses systems, etc. The complex concept design down to system requirements is very much about addressing complexity, making things as simple as they can be while they achieve the purpose. And when you're actually running the system, then of course you have people involved, you have the environment involved, and that's where you again have to address complexity constantly. Here you're addressing complexity early on. So again, Alex McGrath has suggested the use of a particular technique, which is called resilience thinking. And resilience thinking was developed by Brian Walker and David Salt. And they look at projects, systems, etc. as a number of phases. So in phase one, you create a system or you reorganize it in a big way. And that's really about experimentation, about novel and creative ways to move far forward. Then as you have demonstrated that it works, it tends to grow very rapidly. You invest a lot of money, just as they did at the beginning of the railways. And then as they have a very large body of information and tools, etc., you have to start standardize, you have to conserve the system, you have to maintain it, and exercise control over the system. And then at some point, there will be a shock, a system release, and that will trigger fundamental change. Now, at that point, it turns out you will discover whether your original creation of the system has actually been robust and resilient. So complicated problem-solving works really well in this area here, but you have to think about what's going to happen later on if the system has a shock. And so here you've got a non-compliance possibilities, which then creates a shock by having a failure, etc. And if you do that very quick, if you deal with it very quickly, then you get back into reorganization and hopefully some more innovation improving the system so that you can again use complicated problem solving. So it works well in this area. Resilience is demonstrated here, and we really have to make sure that we deal with it properly, because the stress or crisis which occurs here will otherwise not be survived. As I said, it starts very often early on that you have not got enough resilience in your system. And so you have to think about the future while you design your system. So don't make it too complex, don't make it too complicated, because otherwise it will not work. And so here is an example of a slow-moving system-wide crisis which changed the face of the railway industry in Great Britain, the Hatfield derailment. It was a well-known phenomenon. There was a close-coupled system between the wheel and the rail, but there were several organizations managing it, and they didn't achieve rail replacement at the right time. The fault, which of course then caused the derailment, was not properly reported or not understood. And of course, access to the track was limited, and communication through the many different hierarchies was a big problem. A similar incident happened in New Zealand, but in this case, it was a very slow-moving system-wide stress. And people realized it before it actually became a catastrophe, and they very quickly reacted to it. They did the right things, and they caused some difficulties for people, but it wasn't a serious issue. So you can see here a group of people working. And that happened this summer. So a very successful management of a resilience issue. Now, that was sort of the systems engineering aspect. You'll still be getting some systems engineering now later on, but I'm going to talk a little bit about my brother Thomas and myself, because we grew up with a dad who was keen on letting us experience a lot of different things. And so here we are on a train journey, probably when we were about 7 or 8. And it influenced Thomas very much in terms of his artistic work. So this is, of course, a steam locomotive, a freight train, and another steam locomotive, and here an electric passenger train, which of course is a symbol of Switzerland almost, because 99% of the Swiss railway network is electrified. And that of course manifested itself in Thomas's model railway, which had very highly sophisticated homemade electrification. Now, this influenced me to some extent, and Thomas very early decided that he was going to be an electrical engineer, and I then was a bit naughty because before he could study at university, I started, and I just, at the drop of a hat really, decided to study electrical engineering as well. And Thomas always felt that he didn't follow me, I followed him ahead, if you can call it that way. So the schools, I went to school in Zurich, in Switzerland. I studied Latin and Greek, English, etc., etc. I was rubbish at mathematics, and so everybody was expecting me to study a language or the arts. But I decided that I wanted to learn something about math, so I decided to take on an electrical engineering degree. And I did indeed learn a lot about the theory of electricity. But at the end of my studies, I really didn't have a feel at all for what electricity was. I then started to work with GEC Traction in Manchester, as Jason has mentioned. I did practical electricity here, and I really got the feel for it. I then went from thousands of amps to microamps at UMIST for a year, and then I worked as a mechanical engineering researcher at the University of Salford. Following that, I was at Brunel, and I also did a PhD at Brunel. This is an important part of my life, which is why I've got the picture here. I was working at Vulcan Foundry because the locomotives which I was involved with, were being built there rather than in Trafford Park. And this is what's called a man rider, which was used to take miners from the land down underground, deep under the sea, where the coal face was. And so these were being built or rebuilt at Newton-le-Willows, and I was building mining locomotives for the States at the same time. Now, why is this picture important? Well, it's partly or largely because we had Paddy, and Paddy was very important. Paddy was a foreman. He had a reputation for shouting and swearing at every single manager who came on site. And that was because, or his explanation was that he had lost a part of a leg while working for the company, and therefore he was angry with all the managers. So I was 28 at the time. I went to Newton-le-Willows, and I got a stream of words which were largely consisting of the F word. And so I didn't like that very much. Next time I went in, I had prepared myself, and when Paddy started effing, I let loose a stream of filth, which didn't repeat itself, but which lasted for about 2 minutes. Paddy looked at me and said, why do you say that? Why are you talking to me like that? I said, well, you're talking to me in a way that I don't like. So I wanted to show you what it's like. Can we not be friends? And he said, oh, that's a very good idea. And we were friends. So a lesson for life. By the way, Daniel Gooch, who built locomotives for Brunel, was also a time at Newton-le-Willows. So this was the locomotive I built, or rather what all the people around me built. I was just there to make sure that things didn't go wrong. And what I learned at the time was how to build separately excited choppers for traction purposes. And just on reflection, the boy who worked on this is now 40, well, nearly 40 years older. And in that time, we have seen about 7 radically different technologies for traction control. In the same time, Rolls-Royce has had 50 years of evolution of the Trent engine. And if we look at today's Trent engine, it still looks similar to the original one. So no wonder that railways have problems introducing new technology. They do it far too often. I knew at the time that I would never be a teacher because our dad was a teacher and mum was a very bright and competent lady. And so she somehow managed to get us interested in teaching. Thomas and I provided maths tuition for struggling kids. It made a lot of money. And while I was at GEC, I taught literacy and arithmetic with NACRO, the National Association for the Care and Rehabilitation of Offenders. I was then taught classroom control at Salford University with the Kalashnikov approach. And the Kalashnikov approach is not lethal, but it's nearly that, because I was told that in the first lesson you identify the troublemakers, and in the second lesson you talk about something really simple, and exactly at the moment when a troublemaker is not listening, you ask a really stupid question and say, the lady in green. And that's humiliating, and then you have no problems anymore. Then I went to Brunel University, and my boss said, Felix, can you teach computer integrated manufacturing? And I said, what's that? He said, I don't know either, but we have to teach it. It's part of what the industry expects. So I created a new approach to this by using a team-based activity where we built a manufacturing center, and on the right-hand side, you can see one of the groups of people. I think there were 8 in total who I looked after. Fantastic group of people, and I could write my PhD about it. Thomas then said, Felix, there's a job in Switzerland you might be interested in. I'm not. So I said, okay, I'll go and talk to them. And I became a railway inspector with the Swiss government. And here is an example of something I inspected, a level crossing in the Swiss Alps. Fantastic. And that was a very interesting period. But after a year, I realized that I wasn't a civil servant. So I luckily found a job at the University of Sheffield. And here I'm going to give an example of a systems engineering problem which I came across. So a Swiss railway had to create a corridor where out-of-gauge trains, that is very large roll-on, roll-off trains, could run between Italy and Germany and vice versa. And the terrain was difficult, so it was not possible to create 2 tracks which were suitable for these large trains. And so they decided to just accommodate the large trains on 1 track, which could be either the left or the right, depending on the space, and where trains could only accommodate the smaller profile trains, they will put in a safety system. The safety system had to be very basic because neither the locomotives nor the wagons could be modified because otherwise they would be limited to a particular route. So they decided to have an additional signal, which is the violet signal, which was placed in space in areas where the trains could potentially end up in on a track which was not suitable for them, and then they were expecting train drivers to realize that. And so they had a non-secure system, the train describer, which would put the trains normally on the correct track. Now, this is based on the 2-channel safety principle, where you've got, in the UK, for example, a train driver and TPWS. Neither knows what the other does, and therefore it's unlikely that they fail at the same time. So they provide a very high level of safety without actually being failed to safety. And you get very low probabilities of failure. So as an inspector, I was told that the railway had built this as a two-channel safety principle. I disagreed. So the idea was that the route setting was performed automatically, and in 99.x% of the time, it was done correctly. It just very, very occasionally, somebody might put in wrong data or the system might make a mistake. And the train driver was expected to stop, and this was where it fell down, only when he or she saw a lit violet signal and they were at the controls of a loco hauling an out-of-gauge train. If they were at the controls of an ordinary train, then it didn't matter and they had to ignore the violet signal. I didn't like that, as I said. So this is the layout, the typical area of the railway. So you've got the dashed track, which is not acceptable for the large trains, and the ordinary track, which is. And if you look at that, then there are a number of critical points where a train could enter a dangerous area. And in these places, they put violet signals, which would light up if the track was going into the wrong area, both at distant signals and at main signals. And of course, a driver running both out-of-gauge trains and normal trains would be trained effectively to ignore the violet signal. And I did a calculation, and that calculation said that it would take about 14 years to 15 years on average before a driver would actually have to stop the train at the violet signal. Because in a 3-hour period, they would see 17 of those and have to ignore them. So the driver became a backup to a technical system rather than being in parallel. And unfortunately, this summer I discovered that this system had actually been introduced, despite the fact that I had vetoed it. So disappointing. It's only used for very few trains now because there is a base tunnel, but I still think it's not a brilliant idea. So I became an inspector, railway inspector, and then I became an academic because serendipity told me to go to a talk rather than a job interview. Andrew Jablonski then offered me a British Rail funded post at the University of Sheffield to set up an MSc program, and all these people helped setting up the program, and we stayed at Sheffield for 10 years and then went to Birmingham. That gave me lots of opportunities of working with very nice people like Fausto Pedro Garcia. Okay, now how can Porridge be a formal educational enhancement? Well, in 2010, we were already at the University of Birmingham. We had 13 students from Turkish State Railways all together on a cohort of the MSc. And that was a big risk because there were too many people from the same background and too many novices. So we created what became known as the Working Weekend in Wirksworth near Derby to develop team spirit and enthusiasm. And as you can see here, it did create enthusiasm and team spirit. This on the left-hand side is the first group, and then having dinner after the first day's work in a converted dining car, I have to say. And one of the last groups, bottom left-hand corner, where we are having a selfie taken in front of one of our jobs. And Bridget, of course, and I cooking, which impressed the students no end. Porridge is quite good. Anyway, if you want to do these sort of things, you need good and committed educators and trainers. And here we see a particular Mrs. Stakhanov, who does a really good job and demonstrates to the students how to do it. The students felt that this was very rewarding. This person had never held a tool before, and what you can see is she learned it very quickly and becomes quite confident check that she's doing the right job. And by the way, she's now doing a PhD in, I think, Leeds University. Okay, well done, both of you. Their work is mostly hard, but it's also very rewarding. So this is part of our weekend work, and we're all waiting for the next job, which of course is typical for the railway. We also introduced something else in order to teach people more. We started to run technical tours at the end of each MSc program to show people best international practice, and that allows me also to show Charles Watson, one of my colleagues, and Thomas Schmid as a grown-up helping us with these study tours. We have done about 30, and I think the most exciting two were on the maglev train in Germany and flying by helicopter across the Öresund between Sweden and Denmark. We also were asked by Singapore Mass Rapid Transit to help them out because they suddenly realized that a 30-year-old railway is no longer a new railway, so it needed a lot of work. The kit and the people required upgrading, replacing and updating, and particularly in systems thinking. But I just want to, as one of the last few things, to introduce some of my colleagues. Clive Roberts, my boss, the former boss, Pietro Tricoli, electrical, Hong Shin, signaling, Holly, operations. Somewhere is Bridget Eickhoff here, who teaches dynamics. And then over here we have got Clive Cashin, who teaches rolling stock, Zena, who teaches other aspects. And back here again, Charles Watson. And I think it's very important that we realize it's all a team, and it's a team which includes students and staff. The IMechE discovered that I was doing this thing and that I was quite good at it, so they got me involved in running technical tours for the IMechE railway division, and here is a typical one, picture in Ilsenburg in Germany. Very interesting it was too. And the most recent one before lockdown, a technical tour to Czechia, Austria and Switzerland. And I'm trying to highlight here the people who have had connection to the Derby Centre. So hopefully you'll meet them again. These tours are very intensive, and I always end up on the ground taking pictures of track breaks and similar things, or being used as a guinea pig over here as a train moves by at about 50 kilometers per hour on a platform which I don't think would be legal in another country, for example, the UK. I'm very interested in the Railway Children. It's my favorite charity. Here on the left-hand side, it's the Three Peaks by Rail, and the right-hand side is the Railway Sleep Out. I shall be doing one in January, and I shall hope that you will all be sponsoring me. Now back to Sir Arthur Hayward, and this is from his monograph. I think I'm not going to read out these because you can do that faster, but his view of the University of Cambridge was interesting. The new degree of applied science had just made its appearance, in which, in 1871, I had the doubtful credit of appearing alone in the first class. Doubtful because the papers were absurdly simple, and the examiners hardly educated beyond the bare theories of the mechanical process. For it was long anterior to the days of Professor Stewart and his engineering laboratory, where, by the by, I once remember seeing the demonstrator supervising the reduction of a 4-inch shaft on a stout 9 or 10-inch lathe by a young turner whose nervous and thread-like shavings would have ensured his speedy dismissal from any commercial machine shop. I thought that was really lovely. And the whole book, which is called On Minimum Gauge Railways, is really a delight to read. This is words about minimum gauge railways. I venture to think that in the 25 years during which I have devoted much of my time to the subject, in brackets, because I was well funded, I have succeeded in bringing to considerable perfection both permanent way and rolling stock suitable for these diminutive thread lines, and more especially the locomotives, and I'm sure he did. Thank you to all the photographers and many other people, particularly to Sharon Berry, Holly Foss, Francesca, Deborah, Joy, Brian Redfern, who was my mentor, Bridget, of course, who looks after me very, very well, Thomas, my brother, to get me where I am, and Chris Ellis, who was my PhD supervisor at Brunel University. Finally, and I'm sorry about this, I still have to say a few words. We are running a conference on high-speed rail and education at Birmingham. If you're interested, let me know and I'll send you information. And the automated railway seminar is still available online. The cost has now got dropped down post-event. It's an excellent event and I can strongly recommend it. Finally, VAL. VAL is the Railway Division's virtual annual luncheon. It will be on the 5th of March 2021 and it will be very similar to a real one. It will be networking, talking, listening. You'll have to bring your own food, but hopefully you will dress up and so we can even award a prize for that. Please invite your colleagues, please book a table, fix your own food though, own your own drink, and we hope to make a very good surplus for the Railway Benefit Fund and the IMechE support network. Let's hope it's the biggest and best IMechE Railway Division annual luncheon. The table costs just £150 for 10 people. Individuals pay £18 and there are virtual bars, etc., etc., etc. This is the menu, the vegan version, demonstrated by Bridget. Looks quite nice to me, and it was very nice indeed. And the meat-based menu option, you'll be provided with full instructions on how to produce the virtual annual luncheon in real form. Thank you.
Thank you, Felix, for I'll just say a brief thanks now. We'll do more formal one later. But no, thank you very much. That was a really interesting and educational lecture. You said it was going to be, and I certainly personally found that really, really, really good to listen to.
I'm sorry it was so long.
It's fine. We've still got so we're about 10 to 7. We are scheduled to run to half past, so we've got some time. The next order of events is actually questions and answers. So at the moment I can't see anything in my chat panel, so I just need to make sure I'm looking at this correctly. But has anybody got any questions they would like to put to on the session tonight? Yes, okay, right. There's a first question that's come up, so I'll read it out so everyone can hear it and then hand over to Felix. So firstly, thanks very much for an interesting, informative presentation. In the presentation, you mentioned some notable people who made a success from adapting the system, even to the point of having personal hero. You mentioned, for every success, I imagine there are a number of failures. Is there someone in the history of railway engineering that was your nemesis?
Well, I think Brunel was one of the people who really made a lot of mistakes. And we tend to, Eisenbach into Brunel, we tend to think as a real hero of railways, but I think he made significant mistakes, and only Daniel Gooch and his infrastructure engineer saved him from a fate worse than death. However, Mark Eisenbach was helped by Mark Brunel, his father, and I think his father managed to avoid quite a lot of the mistakes. The most amazing thing is the bridge at Maidenhead, which was based on a design by Mark, built by Eisenbach. Eisenbach was very successful financially, and yes, is that a sort of reasonable question, James? Or a reasonable answer, rather?
I think it sounded good to me. James, yes, he's replied yes. That's good.
Yep.
Has anyone else got a question they'd like to put to Felix? Well, I'll fill the time with one I've got myself. So Felix, you quite rightly, it was interesting. I've done a bit of systems engineering myself in the past. It's interesting your discussion around complex and complicated systems and the difficulty in predicting failure, I suppose is the way to put it.
Yeah.
Would you also said in later on that actually we should try and learn as much as we can from systems that are performing as we want them to. Is there anything you'd say around how we would, on the basis, I can understand myself the difficulty in getting to fully understand when something's gone wrong and how that then carries across to say, well, to predict failure in the future. Is there anything to be said for how you best learn when the system's going well and how you then, in the same way, use that learning to predict that the system's going to continue doing well in the future?
So this is based on what's called higher reliability organization thinking. And what Mike and his colleagues discovered was that there are very high risk systems which perform much, much more safely and better than you would ever imagine under the circumstances. He gives examples of flight decks of aircraft carriers, which is the ultimate high risk environment, because if you have a spanner on the deck, then a landing plane will end up in the sea rather than in the nets at the end of the runway. Very good example to my mind, because what he says, what actually happens is culturally everybody on that ship will have as a focus the flight deck, because that's where the biggest risk is. And anybody who walks past, whether it's the admiral of the fleet or a cleaner, will make sure that it's absolutely perfect. And so it's a cultural thing. And he also talks about firefighters in forest fires, which have a huge success rate in terms of surviving by being always totally aware of what's going on around them. And so these people learn from success by constantly observing and always mistrusting success, if that's a way to put it. So things go well, and you ask, why do they go well? And so today, you could say the Deansgate corridor goes well because there are no passengers. But what is actually different? Is it just because people don't behave, or is it because the dispatchers don't do their job properly? And so you can learn a lot from the system going well. Does that sound a reasonable explanation?
Yes, no, that does.
So it's constantly monitor and not trusting old rules. Always review the rules all the time and see, are they still applicable?
Yeah, that's it. Okay, I haven't seen any other questions come through yet, so I'll just wait to see if anyone else is typing. So Peter Woodbridge, I'll just read it out for everybody's benefit. Given that there are normal accidents, are there abnormal accidents, is the question.
Well, I mean, the problem with the terminology by Perrow is that effectively those are things which you don't expect, because a normal accident occurs because, according to reason, all the barriers have failed, but they have failed because the system is so tightly coupled. So the nuclear accident at Chernobyl, for example, even a very small mistake led to a catastrophe because the system had not been thought to ever be at risk from this. And the same for the 3 Mile accident. And Fukushima is probably the easiest to explain, because people had actually designed Fukushima for tsunamis, but they had not gone back far enough in terms of the level of the tsunami. And so when the very high flood wave came, it went over the protective wall, and then of course was trapped. The water was trapped and pumps, and nobody had ever thought that several pumps would fail at the same time. Well, they all failed. So it's a normal accident, which at some point would happen because people had not realized that the tsunamis could be higher. As such, an abnormal accident, to my mind, would be an accident which is planned, which I think is probably a contradiction in terms. Does that sound reasonable, Peter? So a normal accident is something which will, I think the final point is that regardless of the amount of effort and money you spend on it, the accident, an accident will occur at the end. So Stonehaven, there have been a lot of work to try and prevent it. There was drainage because people were aware of the fact that there was more rain. There was a large field which collected a lot of rain, and if it was let down without any protection, it would basically wash down the hill and onto the railway. The drainage which was created was very well meaning. It was probably a very good idea, but it actually then created a concentrated flow of water which could take the ballast which was put on top of the pipe in one fell swoop onto the rails very, very quickly. So it was a normal accident in that sense. Yeah.
Okay, thanks, Felix. And Peter's responded saying that right. Another question from another question's come in. Hi, Felix. Thank you for the talk. In the aviation industry nowadays, aircraft found certain incidents, e.g., containing fan blade failures or fuselage pressure failures. When did the railway industry start building with a focus on containing failure as opposed to avoiding it, and what sort of things were done?
Well, I think there is quite an interesting analogy between the way in which the Shinkansen system was designed and the way in which I would call it the West, but of course it also includes China, has designed trains to introducing crashworthiness was really a containment question. You accept that there is failure potential, so you make the train crashworthy. Of course, the problem with that is you can't actually put enough crashworthiness into a train if you're running at 200 kilometers per hour. If you're very lucky, somehow it goes well, but it's extremely unlikely. So you spend a lot of time, a lot of money, a lot of space on the train to deal with something which could happen. Whereas on the Shinkansen, the culture was always trying to eliminate the possibility of something happening. So yes, there is still a chance, but it's very, very much smaller. So the Japanese don't use bidirectional signaling, even though it's quite a useful thing. But they just say, well, if we do that, then we add risk, which is not necessary. And then, of course, they've got the earthquake issue, so they have to do something about that. But a Shinkansen train, despite the long nose, is not crashworthy. It's not deemed to be a good idea to carrying around crashworthiness for the 25-year life of a train, when you can actually do other things which make a crash very, very unlikely. So there's also, of course, a lot of protection in Japan against derailments, etc. And every morning, basically, a sweeper train goes along the track. It's a characteristic of being able to contain the high-speed rail system. So that would be my answer to the question.
Thanks, Felix. Yeah,
about Murphy's Law.
I think Peter's come back. Peter was a previous, he asked the question originally around abnormal accidents. I think he's come back and said, well, Murphy's Law stands, which is if something can go wrong, it will do. So I guess that's another way of looking at that.
That can be extremely expensive. I mean, at Fukushima, it would have meant building walls around the site which were not 10 meters high, but 15 meters high. And so not thinking about how the plant works properly and not thinking about what are the likely scenarios and just building something which is bigger and hard to beat will still allow Murphy's Law to happen, just in a different way.
Yeah. Okay, got a little bit more time. I think I'll just hold out for a few more minutes to see if anyone else is typing or thinking of a question while we've got the opportunity. I'll just fill the time with one more question myself, Felix, if that's okay. You may be interested in, and probably true comment actually, around obviously people are a key part of any system, and you mentioned, I think the phrase was improving the reliability of passengers. I mean, obviously operators and people part of the system who are following procedures, that's got a level of control, and the system itself, as you said in your lecture, technical engineering systems, there are processes and methodologies to build in tolerances and have the outcomes you're looking for, or reduce the level of uncertainty in them. But obviously people, passengers on our network in the passenger railway are a create a high degree of variability. Have you got any comments on your thinking on, sort of, as you said in the lecture, improving that passenger reliability?
I think an important point is not to assume that everybody is stupid, and building your system on the basis that assuming that everybody is stupid. I mean, I like the example of you have at the station you have a surface which regularly gets wet and slippery, and so you put the yellow sign. And that yellow sign makes everybody careful. Well, it doesn't, because if it's there all the time or 90% of the time, people either think it was forgotten or people think that, it can't be that bad because somebody would have done something about it. Taking away any type of responsibility from the user and from the staff just leads to complacency. I mean, I put that picture of me standing in a very narrow gap between a railing and the platform on purpose. People taunted me to do this, to stand there, to see what it feels like. Well, it doesn't feel very pleasant. And under normal circumstances, I would not go there. But in the UK, we would say, oh, no, you can't stand there. We have to take this away. Bridget and I were just talking today about Oxford Road Station, where a part of the platform is not permitted for passengers. It's about 2.5 meters wide. Well, in most other countries, it would be seen as a fantastic wide platform. When we've seen platforms in Spain which were about this wide, 60 centimeters, and between two trains. So
yeah. No, thanks, Felix. Right, we have got 3 more questions that have come in, so I'll take them in slightly different order to what they've come in. So we've got Ian Walmsley, who's raised one. So presumably having less organisations managing a railway as a system would be a good thing. Yet since the UK railway was split up, safety has improved. Is this coincidence, or what would you expect?
Well, what has actually happened is that the railway has been split up into smaller organizations. So while it is a drawback to have multiple parties, but if you have only 3 smaller parties, let's assume you have got a regional manager responsible for Network Rail for a number of stations. You have a train operator who is largely involved with those stations. You can actually get a dialogue between the two. If you've got a national system which is huge and something is slightly different in one area, that is not going to be considered at the national level because it's too expensive, too difficult. So yes, there is a drawback in splitting up things, but smaller places, smaller systems work better as long as you have got the standards which link them together. So there have to be common standards, there have to be common processes, but local control makes things better. I mean, I shouldn't be saying this, but there are a number of small railways in Germany, in Switzerland, in Austria. They are managed locally, but they follow national rules, and they work very well. And they provide a good level of safety at a reasonable price with good on-time performance, just because they are simple and they're small. So that would be my answer, Mr. Wolseley.
Great, thanks. Thanks, Felix. Right, we'll move to another question while before Ian, if Ian wants to come back with anything. George Fletcher, again, a thank you to Felix. What is your prediction for British Railways after COVID? A new green dawn or another beaching?
I think that's a question, an education question. How can we? I mean, effectively, what we are thinking at the moment is that the market for rail is collapsed. There's hardly anybody travelling. Now we should go back and think what happened before COVID. What proportion of the population travelled by rail? What proportion of people used rail intensively? And you have to say it's probably in London 70 to 80% of people. Elsewhere, 3, 4, 5, 6. And we were often talking about what would happen if double the number of people travelled. Well, the railway network would have had huge difficulties. So I think the market potential post-COVID is still there, and there is building back greener will hopefully use the railways more. So although we say, okay, we won't have the morning peaks anymore, we won't have 5 days a week commuting, well, it will allow lots more people to use railways on 3 days a week in more comfort, while still maintaining the number of travellers, the number of passenger kilometres, just not by the same people, hopefully by a much better market share. And I would work towards that rather than saying, oh, we have to give up, we'll just close the railway. So there's lots of, I mean, Nottingham, Derby to London is a natural rail market, but Nottingham, Derby to Matlock, Nottingham, Derby to Stoke-on-Trent, the rail is actually very competitive on those corridors, but people don't use it because they're not aware of it, or it doesn't run at the time when they need it. So we need to make the railway user-friendly and triple our market share, and it doesn't really matter that there are fewer people travel. Aim for 3 times the market share is my lesson.
Yeah.
And get 2.
Okay, no, thanks Felix, for your thoughts on that. And finally, a question from Andrew Brightmore, taking us back to the systems engineering and the incident accidents piece. Again, thanking you for your time. When considering normal accidents, how does this, if at all, impact how you would approach risk management?
I think there is a big problem in people thinking if I've got a full risk register, then that's fine. How does a risk register, is a risk register established? Well, it's established by looking at history. It's established by brainstorming. It's established by talking to lots of people and then coming up with a register and saying, these are the hazards, these are the probabilities, so therefore this is how we manage risk. And I think that's essential. It still has to be done. But I think observing systems and see how they work well is coming back to that point. Try and observe systems that work well and then find out why they work well and where they might go wrong if there is a small change. The awareness of the risk of change is very, very important. So having a huge increase in water, for example, on the in Scotland, that's obviously a potential risk, which had not been predicted before, really.
Okay. All right. Thank you, Felix, for addressing those. I think that's there's no more questions coming. I'm just conscious of time. We're just this is due to run to 7:30, but I think we're at the limit of questions. So if it's okay, I think I'll bring the question and answer session to an end, and we'll do the vote of thanks, which I'm doing tonight on behalf of the members of the Midland Centre. So Felix, thank you very much for tonight's lecture, and there's your very good. Very good. We can see it. Yeah. No, thanks very much. Really interesting education. I personally found it interesting. I know some of the bits and pieces that you talked about, but it's putting your spin on it and weaving in some of the historical elements made it that much more interesting. We've heard you go run through on the sort of historical development of what is now today sort of railway systems with steel wheels on steel rails, and some interesting points in there. Particularly your bit, and I'll scribble this down, the wheel rail interface at the railhead sees the equivalent of 35,000 bags of sugar, or 280 bags of sugar per square millimetres. I shall remember that little statistic. We talked about systems of systems, and railways anywhere actually, but the British Railways is a good example. You mentioned one of your heroes, Sir Arthur Hayward, who happens to be a local Midlands historical figure, and talking about his development and the book he wrote on minimum gauge railways and the contribution he's made to railways as well. Talks about complicated and complex systems, and this idea that complex systems don't follow predictions, and that perhaps should inform how we think about preventing failures and how we should think about learning from incidents and accidents. And again, that's all very topical at the moment. We heard about some of your career path highlights. You had an interesting and varied career, and how you've done work in GEC and overseas, but your time at universities and obviously the work you've done to set up the MSc programme, which has obviously benefited a lot of students who've been on that programme, but the wider railway industry through the other work you've done and the technical visits that you mentioned, and obviously your contribution and support for charities now. There are 3 key points you mentioned right at the start. Embrace change, think of the value of people, and recognise that education is something worthwhile. I think the thing that came out really is the message to keep things simple, don't make things too complicated or complex. So I think there's some really good points that you've put across tonight. So on behalf of the Midlands Centre, members, guests on the lecture tonight, thank you very much for your time in putting this together and presenting it tonight, and for your questions and answer sessions. And I know we're on a virtual session and we can't get the interaction we normally get for the feedback from the audience, but I'm sure everyone on tonight is thoroughly enjoyed this, and I'm sure we'll get so you'll get that feedback through offline after the event. So just before we close, I'll just to say a couple of final words. So on my behalf as well, thanks to everybody tonight for being on the call and listening. I hope the technology is working. This is the 3rd lecture we've done like this, and while we wouldn't want to be doing it this way, it's actually we seem to be getting into a beat rate with it. So we're able to continue doing these in the current climate. Just a reminder that the Midland Centre programme is available on the IMechE website, so that's got our forward plan for the remaining lectures in this session. And I'll do a quick plug for the next lecture, which is the Wednesday the 9th of December. That's our joint lecture with the Derby Railway Engineering Society, DRES. They are doing a lecture entitled Where Would Railways Have Been Without the Timber Industry, and that's being delivered by Philip Whidden from Nottingham University. That's a 6 o'clock start. It will be on Zoom. A link for the Zoom call will be on the website and emailed out closer to the time when DRES have issued that. But if you're interested in that, that's the next one for us. And another plug, I guess, is other centres have got their lectures available to attend. As I've said before, one of the upsides of the current situation is we're able to join other lectures from around the country, which is a good thing if you're able to do so. So with that, that's all I'm going to say tonight. I hope you've all enjoyed it. Stay well, stay safe in the current climate, and I look forward to hosting another one of these in a month's time before Christmas. Okay, thank you everybody.
Thank you. Good night.